It's my pleasure to introduce Lisa Lynn, visiting here by way of Colorado. She was asking me about the weather here.
It's always like this.
Always like this, yeah. So Lisa completed her bachelor and doctorate degrees in electrical engineering material science at Princeton. And in 2018, she was a hardware engineering intern in the display investigations team at Apple. And then after earning her PhD, she received a director's fellowship to conduct postdoc research at the National Renewable Energy Laboratory. And her expertise, she has a wide range of interests, but her special interests are in low-dimensional hybrid perovskites, and especially as platforms for unique nanoscale light matter interactions, ultrafast phenomena, that hybrid organic-inorganic interfaces, and the design of novel semiconductors for energy conversion and optoelectronics. So this should be a special talk. Appreciate you being here, Lisa.
Yeah. Is this working?
Yeah.
Okay, it is. Okay. Yeah, thank you so much for the invitation to come to Rochester. I enjoyed my visit a lot so far. And I'm really excited to share with you my graduate and my postdoc research on interfacial exciton control for solar energy conversion and optoelectronics. Is this not working? My pointer? Oh, okay. That's weird. Okay. Yeah, so first, just some inspiration, if you will, for studying energy and charge transfer at interfaces. I like this quote from Herbert Kromer, who was the year 2000 Nobel laureate in physics. And he said, the interface is the device. So if we think about any sort of electronic or optical system, there are always going to be multiple functions that your device needs to satisfy. So I like solar cells. So taking that as an example, we need to absorb light. We need to turn those photons into free charge. We need ways of getting that charge out of the device. So those are all different functions. And it's really hard to come up with one material that's going to satisfy all of the needs of your device. So what we tend to do is create these modular multi-component systems where different materials have been optimized to different purposes. But as a result, you end up with interfaces. And all of those components need to work together. They need to talk to each other. And that communication is often done through energy and charge transfer at these interfaces. So I think there's a lot of really interesting and important work that is to be done in studying both the basic photophysics of these energy transfer processes, but also how they work and contribute to device function as a whole. Yeah, so a lot of my past research has been inspired by renewable energy conversion. So I want to start with a discussion of some fundamental efficiency losses in solar cells. So this is sometimes called the Shockley-Queisser limit after the two authors of the original publication in 1961. And what they found was that a maximum of about 34% of your incident sunlight can be converted into electrical power. So the breakdown of the losses in the solar cell can be shown here in the chart on the right. So this number is a function of the band gap of your absorber. So everything in green is good. That's what you can get out of the solar cell. And everything else is a loss. So just looking at this chart, clearly there are two sources of loss that overwhelmingly dominate. First, we have transmission losses shown in red, and then the thermalization losses shown in yellow. So both of these losses come from the fact that solar cells are made out of semiconductors that have a band gap. So any photons with energy below your band gap don't get absorbed. Those are your subband gap transmission losses. And then any photons with energy above the band gap, while they do get absorbed, a lot of that excess energy gets rapidly thermalized as your excitation relaxes to the conduction band edge. Right, so if there's anything we can do to try and mitigate either the thermalization losses or the transmission losses, this can potentially bring our solar cells beyond the so-called Shockley-Queisser limit of 34%. So over the years, scientists have come up with some clever ways of doing that. And my graduate research was focused on organic solar cells that used multiple exciton effects to try and combat some of these fundamental losses. So the two multiple exciton effects that I want to discuss are singlet fission and triplet-triple annihilation upconversion. So these are photophysical processes that happen in certain special organic semiconductors. I'm showing an example of pentacene undergoing singlet fission and parylene undergoing triplet-triple annihilation upconversion. So in the case of singlet fission, after photoexciting one of these pentacene molecules, that energy can then be divided between two lower energy triplets now residing on neighboring pentacene molecules. And then triplet-triple annihilation upconversion is the opposite process, where you start with two triplet excitons, and they can actually pool their energy together to create one high energy singlet, and then the other parylene molecule relaxes to its ground state. So let's take a look at how both of these multiple exciton effects can improve the performance of our solar cells. So in the first example, I want to discuss singlet fission solar cells. So here I have a very conventional organic solar cell heterojunction where we have an electron donor and an electron acceptor. And both of these materials can absorb light independently. And then at the interface between them, we have a charge transfer state that turns those bound excitons into free charge. Now, in the singlet fission solar cell, we add an additional component that's able to undergo singlet fission. So it absorbs blue light, produces triplets that are then transmitted into the main solar cell for dissociation. And if we take a look at the green photons that this normal solar cell is able to absorb, by adding this singlet fission sensitizer, we're also able to take advantage of some high energy blue photons that previously would have been thermalized, right? So the singlet fission solar cell gives us a way of combating these above band gap thermalization losses. The next type of solar cell is an organic intermediate band solar cell. Again, we have the classic donor acceptor configuration for the solar cell, but now one of the layers, in this case the donor, is able to perform triplet-triple annihilation upconversion. And we're adding an additional component here, a triplet sensitizer that can absorb low energy red photons, perform intersystem crossing to transmit triplets into our upconverting layer, all right? So now, in addition to the green photons that this normal solar cell can absorb, by adding this upconversion process, we're able to take advantage of some low energy red photons that previously would have been transmitted. All right, so both of these types of solar cells give us ways of combating both the thermalization losses and the transmission losses that conventional solar cells would experience. All right, so I know I'm a few slides in, but this is where I want to introduce the agenda for my talk. And I like to keep these schematics up here so I can point to the various interfaces and parts of the devices that I've studied over the years. So first, I'm going to talk about one aspect of my graduate work, looking at the effect of nanoscale morphology on the energetics of donor-acceptor CT states. Second, I'll discuss our work developing a solid-state implementation of this organic intermediate band solar cell. And finally, I'll discuss my more recent postdoc work at NREL, looking at novel routes for triplet sensitization using hybrid perovskites. All right, so first up is the effect of nanoscale morphology on the energetics of donor-acceptor charge transfer states. So something I didn't really emphasize earlier, but is actually quite important in both of these types of solar cells, is the relative alignment of this donor-acceptor charge transfer state with respect to the singlet and triplet levels of our various constituent materials. Right, so for the singlet fission solar cell, in order to actually take advantage of the triplets that are being generated through fission, we need this donor-acceptor CT state to lie lower in energy than the triplet of our fission material. On the other hand, for this organic intermediate band solar cell, we want to restrict the photocurrent generation only to the singlets that have been produced through this upconversion process. And as a result, we want our donor acceptor CT state to lie somewhere in between the singlet and triplet states of our upconversion material. And researchers have found over the years that both the molecular orbital energies as well as the interfacial charge transfer state energy is highly dependent on morphology. So it'll depend on things like the local dielectric environment at this interface, the molecular orientation, as well as the degree of structural order and the degree of charge delocalization at this interface. So going back to the singlet fission solar cell, here I have a simplified schematic for the device. We have a material that's able to undergo singlet fission to produce these low energy triplets. And then again, we want our donor acceptor CT state to lie somewhere below the triplet level of that fission material in order to actually extract those excitons as free charge. So this schematic is good, but if we have a donor acceptor CT state that's somewhere up here, we're not actually able to take advantage of the fission process. So first we studied a singlet fission semiconductor called rubrene. So it's this tetracene derivative that has 4 phenyl groups hanging off of it. And my colleague Mike Fusella found that with a fairly simple heat treatment, you could transform as deposited amorphous rubrene films into this nice crystalline morphology. And when we look at the molecular orbital levels associated with these 2 different films, we see pretty significant differences of a couple of 100 millieV in the 2 different systems. Now, to actually build our solar cell, we need to introduce an electron acceptor. We're using C60 as our electron acceptor. So here I have the HOMO and LUMO diagram for the resulting solar cell. And both the rubrene and the C60 can individually absorb light. And then you can also absorb directly into the interface between the donor and the acceptor. And this results in a low energy absorption feature beyond the spectra of either rubrene or C60 by themselves. And we can look at the photocurrent that's being produced by the device as we photoexcite it with different wavelengths of light. So here on the chart, I'm showing a log or semi-log scale of the photocurrent output from the crystalline and the amorphous rubrene C60 devices. And if we focus on the low energy region down here, we can see that they have quite different shapes. So this low energy region can be fit to Marcus theory of electron transfer to extract the charge transfer state energies associated with both of these interfaces. And from that, we can build the Jablonski diagrams for both amorphous rubrene and the crystalline rubrene C60 interfaces. And we see something interesting, all right? So for the amorphous rubrene C60 device, the charge transfer state energy that we fit is actually higher in energy than the triplet of rubrene. So even though rubrene is undergoing singlet fission, producing all these triplets, we're not actually able to extract those triplets as charge, right? On the other hand, for the crystalline rubrene C60 device, the resulting charge transfer state energy is somewhat lower, so we're able to take advantage of the fission process. So the key takeaway from this study was that even though we have 2 devices that have exactly the same constituent materials, exactly the same layer structure, just because of this morphology difference at the interface, only the crystalline rubrene C60 solar cell actually functions as a singlet fission solar cell. And I think at the time, this was not widely appreciated by the community. In addition to rubrene, we did some systematic studies on another singlet fission material called pentacene. So it's a linear acene with 5 rings. And we looked at different underlayers. So we used plain indium tin oxide as our substrate, as well as ITO that had been coated with P.PSS P3HT, which is a very common hole extraction material in these solar cells. We created what's called a discrete donor acceptor heterojunction, where you deposit pentacene, then you sequentially deposit C60, and you essentially have a planar heterojunction between the 2 materials, as well as what's called co-evaporated bulk heterojunctions, where your molecules are evaporated at different ratios together. So you get a nice mixture of the 2. And from the atomic force microscopy images, you can see that there's quite a range of morphologies being produced through these different methods. And we can go through the same exercise again, where we build the solar cells, characterize the charge transfer state energies of these interfaces, And in general, what we see is that when there's enhanced structural order at this donor-acceptor interface, this is linked to a lower charge transfer state energy that's more likely to extract the triplets that are being generated by the fission material. Okay, so that concludes the first section of my talk on the effect of nanoscale morphology on the energetics of donor-acceptor CT states. And the two key takeaways are that essentially the interface morphology in these devices can make or break your singlet fission solar cells, and that having enhanced structural order at the interface is linked to lower charge transfer state energies. Moving on, now I'll discuss the work that we did developing a solid-state organic intermediate band solar cell. So here again is the Jablonski diagram for the organic intermediate band solar cell. We have the classic donor-acceptor configuration, where one of the layers, in this case the donor, is able to perform triplet-triple annihilation upconversion. And then we have a triplet sensitizer that can assist in populating the triplet levels of our donor. Now, just looking at this, you can see that there are a lot of energy levels involved, and they all need to work together to make the device function as a whole. So one of the big challenges initially was identifying a material system that would give us these energetic requirements. So we're going to focus on this triplet sensitized upconversion subsystem first and ignore the acceptor for a second. And the sensitizer we identified was PT-TBBP, which is a porphyrin compound, as a platinum atom at the center. And because of this heavy atom, it can induce intersystem crossing with high efficiency. And then the upconversion material is alpha-sexothiophene, or alpha-6T. So we want to prove that the photophysics of this upconversion subsystem are operative. And to do that, we turn to transient absorption spectroscopy. So if anyone's not familiar with this technique, it's a pump probe spectroscopy technique that allows you to observe the evolution of excited states in your system. And when we look at the transient absorption spectra of just this platinum porphyrin compound by itself, when it's been embedded in an inert matrix and all the molecules are separated from one another, we see really long-lived triplet features. So the purple trace here is 5 nanoseconds, or 5,000 picoseconds, and you can see that there's significant amplitude at 5 nanoseconds. However, when we embed PT-TBBP within alpha-6T, the amplitude of the signal is significantly quenched, which suggests that the energy is being transferred from the triplet of PT-TBBP elsewhere. And the answer is that it's moving over to the triplet state of alpha-6T. All right. So after proving that we're populating the triplet levels of alpha-6T, we need to show that upconversion is actually happening. And for that, we turn to delayed fluorescence spectroscopy. So we photoexcited this mixed film at a wavelength that's selectively absorbed by the platinum porphyrin compound at 633 nanometers of light. And the emission is shown in the top panel here. And you'll notice that the emission from the system is actually coming at a shorter wavelength, or a higher energy, compared to the excitation. So that's a clear indication that upconversion has occurred. All right. And then the spectral shape of the emission also matches that of the direct emission from alpha-6T. So we know that it's coming from the same species, in this case, the alpha-6T singlets. Another test of triplet-triple annihilation upconversion is to look at the power dependence of your emission. All right. So triplet-triple annihilation upconversion is a bimolecular process. So at least initially it has this quadratic dependence on your incident power. And when we plot the power dependence of our emission, which is shown in black, you can see that has a log-log slope close to 2. So that is indicative of this bimolecular process. On the other hand, the direct fluorescence from alpha-6T is shown in red and has this classic linear dependence. All right, so we can be satisfied that this Jablonski diagram is correct in our system. And the next step would be to build the actual solar cell by introducing an electron acceptor. So we identified diindenoparylene, or DIP, as an appropriate acceptor for this type of device. And to prove that photocurrent generation due to absorption events on the platinum porphyrin compound were actually leading to free charge in the system, we introduced a neat alpha 6T spacer of varying thickness to separate the site of sensitization from the site of charge dissociation. And here I'm showing a zoom in of the photocurrent output from the solar cell in the wavelength region where the platinum porphyrin compound is absorbing. And even when this spacer thickness is as big as 60 nanometers, we're still seeing a little bit of photocurrent contribution from the PT-TBBP. So we can be satisfied that the entire device is operative as we expect. As an additional proof of the mechanism, we also performed some comparative studies with a related but slightly different solar cell called the triplet sensitized solar cell. So in this device, we're replacing DIP as our acceptor with C60. And instead of getting a donor acceptor charge transfer state that is higher in energy than the triplet of alpha 6T, we now have a charge transfer state energy that is lower and can collect both singlets and triplets from the alpha 6T. And the reason why this is an interesting comparison is because now if we were to modulate the rate of triplet-triplet annihilation in both of these devices, we expect it to have different effects on the photocurrent. So for the intermediate band solar cell, because only charge dissociation can occur from the singlet level, the more TTA we have, the more singlets we produce, and that's going to give us more photocurrent. So it should enhance the photocurrent. However, for the triplet sensitized solar cell, every TTA event is taking away 2 triplets that could have led to charge and producing only 1 singlet. So we expect TTA to actually detract from the photocurrent. So the way we modulated triplet-triplet annihilation in these devices was by applying a background light to the system. So remember I said that TTA is a bimolecular process, so it depends on the density of excitons that are present. So when we apply this background light, we expect to increase the rate of triplet-triplet annihilation. And for the intermediate band solar cell, where we expect that to enhance the photocurrent, as we increase the background light power, we see a rise in the photocurrent production and eventually a drop off. However, for the triplet sensitized solar cell, the increased triplet-triplet annihilation produces a decrease in the photocurrent as we expect. So this, at least initially, is in line with our expectations. But we did have the question of why there was this drop-off in performance for the intermediate band solar cell as we moved to higher background light intensities. And our hypothesis was that the device was now suffering from exciton polaron annihilation. So as you flood the system with extra light, you're also producing a lot more polarons that can now interact with the excitons that are being probed and annihilate. So to test this, we applied a modest voltage bias to the solar cell at the same time. And we applied a reverse bias that basically sucks the polarons out of the device more quickly, so they have less time to interact with the excitons being probed. And you can see that the drop-off is now reduced in this red curve. On the other hand, when we apply a forward bias, that's going to inhibit polaron extraction, and you can see the drop-off is more severe. Now, I like to mention that this is my favorite data set that I collected as a grad student, because it's not often that you have an experiment that verifies your hypotheses as well as it did in this case. So I like this chart. Yeah, so that concludes the second part of my talk, discussing this solid-state organic intermediate band solar cell. First, we used transient absorption spectroscopy and delayed fluorescence spectroscopy to prove the photophysics in the system, and then various device studies to confirm that photocurrent generation was possible through this triplet-triplet annihilation upconversion process. And finally, because this was a novel device concept and implementation, I'm also proud that we were able to file a patent for this work. Okay, so That brings me to my postdoc work more recently at NREL, looking at novel routes for triplet sensitization using layered 2D hybrid perovskites. So I want to take a step back for a second and just talk about triplet sensitization more generally. So molecular triplets have many useful properties. For example, their statistical abundance, as the name suggests, there are 3 triplets that exist for every singlet. They tend to have long lifetimes because relaxation of a triplet excited state to a singlet ground state is spin disallowed, so it tends to happen more slowly. And then triplets are involved in some really unique spin interactions, like singlet fission and triplet-triplet annihilation, which I discussed earlier. Now, one of the big challenges with using triplets, especially for optical applications, is that you typically can't directly photoexcite to a triplet state because that's also spin disallowed. So what we typically do is introduce a triplet sensitizer. So that's another molecule or thing that's able to absorb light and then produce triplets with high efficiency and ideally with low energy loss. So if we think about the qualities that we want in a triplet sensitizer, first we want it to have broad and strong absorption. We want the intersystem crossing to be very efficient. We want a low singlet to triplet energy difference so that we can minimize the energy that's being lost in the process. And then finally, from an engineering or practical standpoint, it's nice when these things are low cost and easy to synthesize. So here on the right, I have various types of triplet photosensitizers that have been studied and developed over the years. They all have their pros and cons in terms of this wish list. So metal organic complexes like the porphyrin I mentioned earlier. There are also what's called thermally activated delayed fluorescence compounds, and then also nanoparticles and quantum dots, which are really nice because they have these like really size-dependent optical properties, so you can really tailor your sensitizer to whatever application you're dealing with. So they all have their pros and cons. Over the last decade or so, I would say, people have started to realize that these hybrid perovskite semiconductors are really great platforms for triplet sensitization. So here I'm showing a cartoon of the crystal structure for a low dimensional version of this metal halide perovskite, where you have these inorganic metal halide sheets, which are the blue and the gray atoms, and they're separated from one another by organic molecules shown in green. All right. So what's really nice is these are excitonic materials. So again, they have very tunable properties. And the presence of the heavy atoms in the metal and the halogen sites can induce spin mixing of your exciton within that layer. And then with an appropriately chosen organic chromophore, we can now try and drive a triplet energy transfer across the interface. So I want to talk specifically about a naphthalene-based lead bromide 2D perovskite composition. The energy diagram is shown down here on the bottom right. So the exciton band for a single layer of lead bromide is around 3 eV, and then the triplet state for naphthalene is around 2.6 eV. So that gives us a pretty substantial driving force for triplet energy transfer across this interface. Now, you might expect the next step to happen is for naphthalene to just phosphoresce from its triplet state. And indeed, it has really strong room temperature luminescence, as you can see on the figure here on the right. But that's not actually what happens. Instead, the naphthalene tends to couple to another naphthalene in its ground state to form a triplet excimer. And that ends up being the final luminescent state in the system. Now, excimer formation is highly orientation dependent. So here I've pulled a figure from a work where the authors looked at a series of L-shaped naphthalene dimers. And depending on the rigidity of the dimer and the tilt angle between the chromophores, you see a transition in the photoluminescence from the monomeric behavior, which are the spiky spectra at the top, to the broad exomeric emissions that you see at the bottom, all right? So there are a lot of morphology considerations here when it comes to what's dominating the luminescence of your films. And when we look at the perovskite PL in this figure, clearly the spectra is more exomeric. So because of this, we had a question of whether we can control photophysical outcomes in these materials through interfacial energetics. So one of the things people love about these hybrid perovskites so much is how tunable their optical properties are. So we can mix the halide site in these perovskites from chloride to iodide to bromide to get really nice transitions in their exciton energies. So for the pure bromide system, which is shown in red, we have an exciton transition close to 400 nanometers. And then for the pure iodide system, we have a much lower energy exciton around 500 nanometers. And then the resulting interfacial energy level alignment looks like this, where for the pure bromide system, we have a large energy driving force for triplet transfer. For the pure iodide system, that process is unfavorable. And then for some of these intermediate bromide to iodide compositions, we may reach something of a resonance condition across this interface. And when we look at the photoluminescence from this series of perovskites, what we find is that it's essentially consistent with our expectations. The pure bromide system shows mostly naphthalene triplet-based emissions. That one's shown in red. For the pure iodide system, we see only emission from the inorganic exciton because there is no triplet transfer to naphthalene. And then for some of the intermediate combinations, we see both inorganic exciton emission as well as naphthalene-based emissions. Now, if you had sharp eyes, you might have noticed there's actually two extra peaks that have popped up in the spectra for the orange and the green curves, located at around 495 and 510 nanometers. The fact that they're so sharp and closely spaced means that they're unlikely to originate from an excimer, which tend to have really broad, unstructured spectra. And if we look in the literature, the location of these peaks is actually an exact match with the monomer phosphorescence from naphthalene. And if we go back to the energy band diagrams, we can understand what's going on here. So for these intermediate compounds shown in orange and green, the exciton band in the lead halide is pretty close in energy to the triplet of naphthalene, such that we might even have some back and forth energy transfer across this interface. And this reversible energy transfer allows the monomer phosphorescence at 495 and 510 nanometers to compete with the excimer formation. So that's why we start to see these extra features showing up in these spectra. Finally, we can use ultrafast transient absorption spectroscopy to understand the interfacial dynamics in these systems. I have a note up here in blue for anyone who's not familiar with the data analysis for transient absorption spectroscopy. But when you see a negative feature, it tells you that something is leaving its ground state. And when you see a positive feature, it means that some sort of excited state is now absorbing. Right? So here I have the transient absorption spectra for one of the perovskite compounds. And frankly, the TA spectra for a lot of perovskites are kind of boring. You just see like a really strong exciton ground state bleach that tells you they're leaving their ground state. But in addition to this ground state bleach, we also see a broad photoinduced absorption feature at long wavelengths beyond the bleach. Now here I have stacked the transient absorption spectra for all of the compounds, and I do apologize, it's impossible to see any sort of detail here on the left, but I'm showing a zoom in of some of the spectra here in the center. And what we noted was that for all of the bromide-rich compounds for which triplet transfer to naphthalene was favorable, we see this broad photoinduced absorption feature. However, for the pure iodide system where we don't expect any triplet transfer, there's also no photoinduced absorption. So at least qualitatively, we can conclude that this broad photoinduced absorption feature is related to the naphthalene triplet species being populated. We can also take a kinetic slice in the middle of these spectra to look at the kinetics of this PIA formation. So for the pure bromide system, which is the curve shown in red, this signal reaches its maximum at ultrafast timescales within the instrument response time. However, for some of the intermediate bromide to iodide compositions where triplet energy transfer might be a bit slower, because the energetic driving force is smaller, we can see that the signal is reaching its maximum at a slight delay, somewhere between 1 and 10 picoseconds. All right. So what we learned from this study essentially is that both the interfacial energetics and the resulting driving force for triplet transfer affects both the luminescence outcomes in these materials, as well as the dynamics at the interface. Another thing we learned is that it's really hard to get away from this excimer formation, which makes sense because you have all these conjugated molecules that have been stuffed together in a solid state structure. So they're going to want to interact with each other. So as a follow-up to this, we were interested in whether we could control these intermolecular interactions through organic cation mixing. So remember I said perovskites are incredibly tunable, and in the last study, we showed how we can change the halide composition to get different optical properties. There's also no reason why the organic part of the perovskite needs to all be the same. All right, so here we borrowed a concept that's often used in organic electronics called the guest-host concept, where if you have a phosphorescent guest emitter, you surround it with an inert molecule, really inert high band gap molecule, in order to protect this chromophore from unwanted quenching interactions with its environment. So again, we're using naphthalene as our phosphorescent molecule, but we're surrounding it with a lot of this saturated alkylamine, hexylamine, in order to protect it from some of these intermolecular interactions. And I made a series of these perovskites, and the point of this absorbance and thin film XRD are just to show that there's no obvious phase segregation, which would show up as peak splitting in the absorbance and XRD peaks. So now let's take a look at the photoluminescence from these compounds in turn. So for the pure hexyl ammonium lead bromide perovskite, all of the emission that we see is coming from the lead bromide framework. All right, so we see emission from the free exciton, which is the part shaded in blue, as well as what's called a self-trapped exciton. So these are really soft lattices. So the exciton can actually get trapped by its own potential, and it produces this really broad red-shifted emission, which is the part shaded in green. But there's no emission coming from the organic part because we don't expect any interaction at this interface. For the pure naphthalene lead bromide perovskite, we see something familiar. So this looks like what I showed in the previous study. There's very little emission from the inorganic exciton, and then most of the emission is coming from naphthalene triplet excimers. And then finally, when we mix the two organic molecules together, we see emission from 3 different species. First, we see pretty significant inorganic exciton emission. Then we also see naphthalene monomer phosphorescence, which is the part shaded in orange. And then we also see some eximeric contributions as well, which is the part shaded in red. Now, when I plot the spectra associated with these 3 compounds together, you can see just how different they are. All right, so we have the pure naphthalene system, which is the spectra in black, the pure hexylammonium system, which is the curve in blue, and then the mixed one is the red curve. And the color coordinates associated with each of these spectra vary anywhere from green to yellow to orange, depending on the organic composition. And you can also see some photographs down here for the orange and the green emitting films. So I think these 2D hybrid perovskites are a really exciting platform for achieving this like wide emission color tunability, where you can play around with the different species that are emitting in order to get any desired color. And finally, we can look at the interlayer energy transfer dynamics in these systems through time-resolved PL. So here I have a streak camera image for one of the mixed cation systems, and you see a really rapid decay of the inorganic exciton centered at around 410 nanometers, and then a really long-lived molecular emission, which is consistent with its triplet character. Now, this time scale is around 200 nanoseconds, but we had up to 200 microseconds on our streak camera, and even at 200 microseconds, there was no significant decay of this molecular emission. So in order to actually analyze what's going on at short timescales, I'm going to subtract that as a constant background, and the resulting curve is shown in red. So there's some interesting things to note here. First of all, like I said, there's a fast decay of the inorganic exciton, which is consistent with the energy transfer into the organic layer. And then there's also a subtle rise time present in the molecular emission, which you might be able to see slightly in this red curve. That again is indicative of the energy transfer process. And then finally, if I were to calculate the average time constant associated with the inorganic exciton decay in this series of perovskites, and we see this nice trend where for the hexyl ammonium, it has the highest average time constant. For the pure naphthalene system, it has the shortest. And then the rest of the trend is reflecting the amount of interfacial area that is available for the energy transfer. Okay, so that concludes the last section of my talk on novel routes for triplet sensitization using layered 2D hybrid perovskites. I think these 2D perovskites are a really cool and versatile self-assembled framework for triplet sensitization, and something I'm really excited to continue studying in the future. What we've found through our work is that the luminescence behavior in these materials is often dominated by intermolecular interactions. And we can tune the energetic driving force for the triplet transfer at this interface, and that controls both the static luminescence spectra, as well as the kinetics of energy transfer. And finally, I'm really excited about organic cation mixing as a strategy for controlling intermolecular interactions in order to get wide color tunability in these materials. Okay, so that concludes my talk. I have a lot of wonderful scientists to acknowledge over the years that I've been able to work with, especially my PhD advisor, Barry Rand at Princeton, as well as my postdoc mentor, Justin Johnson at NREL. And these are some of our collaborators that we've worked with and their institutions. And the funding for this work came from the NSF, the US Department of Energy, and I'm also grateful for the fellowships that supported my graduate and postdoc work. And thank you for your attention. Thank you for inviting me to Rochester.
Thank you. Questions?
So, I mean, you discussed several ways to make better solar cells using organic materials and perovskites kind of materials. So my first question is, how much do they improve compared to silicon? I mean, silicon, you said there was a limit about 34% or something maximum you can get. Do they bring us to 50 or 60%? How much do they improve?
So the two next generation device concepts that I introduced, singlet fission and upconversion solar cells, theoretically, they could get to around 42. I think that's the number. So that's how much they would add. Practically, we didn't achieve that. I think at least our organic intermediate band solar cell is more of a proof of concept. And obviously there's a lot of work to actually, bring it to those kinds of efficiencies. But just in general, people have come up with other configurations like multi-junction tandem solar cells, where combined, if you take perovskite as an absorber and combined it with silicon in a tandem configuration, that can actually exceed the single junction efficiency limit for silicon itself. So that has been achieved.
So commercially, only silicon solar cells are commercial, right? I mean, nothing else is out in the market besides silicon?
There are a lot of startups working on perovskite and perovskite silicon tandem.
And you think they will be competitive cost-wise, they will be similar cost, or I mean, to be successful, I mean, the cost has to be similar too, I mean, right?
So one of the big selling points for perovskites is the cheap processability.
I see.
I don't really know what the state of the industry is, if people have actually brought costs down that much. But I know research level cells have exceeded silicon efficiencies. Yeah.
Thank you.
Yeah.
So you mentioned in the fission process
Mhm.
that the surface morphology plays a role. And is it true that it's the correlation, I'll call it the coherence of the morphology? Is it the depth? What are the components of the structure that then add to that process?
Do you mean like how uniform does the
Well, so I mean,
morphology be, or-
morphology has a lot of different
Okay,
kind of
yeah.
ways to describe it, and it's the question of, as I saw it, you indicated that morphology helped, or a structured system helped. Yes, I'm wondering what component of the structure was that which correlated to improved performance? So that's one question. And then the second question, would it also be possible to use surface structure to help with perovskites?
Okay, so for the first question, I think it's almost at like the molecular level. We're not talking about structural order on the tens of nanometers length scale away from the interface. Because the charge transfer state is still fairly localized. It's not, extending multiple nanometers away from the donor acceptor interface. So having the crystalline rubrine morphology, just, we didn't really pair our experimental work with like computational studies to like truly look at the effect of molecular orientation, but our hypothesis was that it would put the rubrine molecules in a nice alignment with respect to C60. C60 is just round, so it doesn't really have too much morphology. But the rubrine would be lying in a nice way at the interface in order to stabilize the charge transfer state energies. That was kind of our hypothesis. But people are still kind of working on this question. I think it's not completely understood, like what's contributing to the changes in the molecular orbital energies and the resultant CT states.
Would that
Yeah.
kind of engineering help with the perovskites at all?
I think it would. It's always good to play around with the morphology of your films when you make device structures. There's a lot of optimization you can always do. Like at the kind of length scales that we're dealing with here in the perovskites, I don't think the overall film morphology contributes too much. It might help with like scattering or outcoupling of the light, if you had a smoother film versus something very disordered. But we're dealing with very small length scales when we talk about these interfacial energy transfer processes. Probably on the order of like 10 nanometers or so.
Thank you.
Yeah, it just seems to be like some of the battles that you're facing here, you're going through here, are similar to what they would have gone through for OLEDs, right? For organic LEDs, in like the thermal problems and making contacts and all those things and fighting all these other things that you don't want. But the OLEDs have been very, very successful commercially, even quite large screens and cell phones and stuff.
Yeah.
Can you say really at a high level, is this a lot harder than making an OLED that emits light? Is it a lot harder than making something that takes light and converts to energy? It seems like it's exactly the opposite problem. Just at a high level, how are they similar or different?
I think there are definitely a lot of parallels, and I'd be excited to see like inkjet printed perovskite, emitters in the future. But yeah,
It could be if the sun emitted only red, green, and blue. Well, that could have 100% efficiency.
And the second question, so I know, my dad worked in photosynthesis for many years in excitons, and he used to say that if you're studying photosynthesis, you're studying all these energy transfer mechanisms. If you're doing it by looking at fluorescence, then it's kind of like trying to figure out what a scientist does, and you go in their office and you only look in the trash can, right? Because you only look at all the stuff they threw out. Okay, so what he was saying was that in photosynthesis, the goal is light comes in And then, energy,
Yeah.
energy comes out, right? So the leaf grows, okay? So in your case, it seems very similar, right? So I was a little surprised that you switched to fluorescence at the end and started talking about that, because that's looking in the trash can, isn't it? So what do you have to say about that?
Well,
He might be online, by the way, I'm not sure. So go ahead.
So to the question of fluorescence versus like, I guess, phosphorescence or keeping
Current measurements, yeah.
yeah, so all of the work I discussed with the perovskites, those are not devices, they're literally just films. Yeah, so I think there's a lot of work that can be done, to actually, go towards the device integration. But what I think is really cool is that we can play around with the different species that are emitting. So we can have singlets undergoing fluorescence, or we can have triplets undergoing phosphorescence, and they occupy different parts of the spectra. And you can kind of combine them and hopefully use that combination to produce any sort of color emission that you desire. So that's what I'm really
Well, no,
excited.
really, what I'm asking here is, would you say the same thing, that if your device is emitting light, then it's wasting energy, right? Because you're trying to make a solar cell, not an OLED, right? That's really what I'm. Yeah.
Well, a good solar cell is also a good LED is also a good solar cell.
What I'm really asking, yeah, right, yeah.
Yeah, like if basically if your energy can be funneled into something radiative instead of something non-radiative, that's always a good thing. So I think just because the system is emitting light doesn't mean that, you're, I don't know.
So Duncan Moore has a question online. What are the Fresnel losses for these materials? Like from the Fresnel reflections?
Oh, okay. Are we talking about the perovskite work or the organic solar cell configurations or?
Yeah.
Well, this is Duncan Moore. What I'm curious about is as the light comes into the device, there's a Fresnel loss. And that's dependent upon the index of refraction. And so the question is, if you end up going to production, and I know you're a long way away from that, but are these cells going to have to be AR coded in order to maximize the throughput?
That sounds like it would help. In the research that I did, I never pursued any sort of experiment like that to try and understand what the reflection losses would be. At some point, we did try to measure like the internal quantum efficiency for the solar cells that I presented in the first half of my talk. Like using a integrating sphere, you can try and measure what's being reflected off of it. But honestly, I don't really remember what kind of numbers we were getting.
Okay.
But
Thank you.
yeah.
Are there values of, is refractive index measurement of a film something that is straightforward to do? Is that a technique that you use?
I think it should be like pretty straightforward to do, but I
would think that at least 2.
Yeah.
Effective index will be about 2. That's a 25% loss. Easily, from that.
But if you put it on top of silicon,
right.
can it give you an AR code?
Yeah, that's right. Yeah. So there are
There may be ways to put it.
See a question here. Okay.
See, silicon wants the square root of 3.5, right? For
Yeah.
perfect AR.
That could be modification. Yeah.
Okay.
It's a long.
No question.
Comment here, but yeah.
So, did you read it?
You read it, Tom?
Maybe you can read it.
I have about 4.5 years of experience using confocal spectroscopic techniques. Measure the photodynamics of 3D lead halide in the process of wrapping them for problem. You can only very well do research. Okay, that's a good compliment. I was wondering if there's a question there.
I don't think so. Let's see.
You can thank them for the
Yeah,
compliment.
thank you. I don't know
You
where the
make an
camera is,
excellent
but
videographer. Okay. All right.
yeah, great.
Your first.
Sounds
Yes,
good.
Doc.
All right, any other questions? All right, if not, thank you so much.
Yeah.
Thank
Thank you.